Hello everyone. So today we are back with another video lecture. So today what we will do is we will discuss gradient tapes. So this is very important concept in TensorFlow. So what basically it is basically used for TensorFlow gradient tape actually records operation for automatic differentiation. So what exactly it is doing is when you go for any deep learning architecture, whether it's neural network or convolutional neural network or generative adversarial networks or any advanced networks in the area of machine learning and deep learning, normally what we do is we do the learning process, and that learning process is done through backpropagation. So backpropagation actually is nothing but it's a series of derivatives which we take for the parameters which will be updated in the due course of time. So somewhere or the other, gradient tapes are basically used for calculating these derivatives and keeping track of that. So what exactly it is doing is it actually watches the operations executed within its context, and it builds a computational graph which is then used to compute gradients of the variables with respect to the some loss or output. So what exactly I'm trying to say here is that suppose if you have a machine learning architecture, let us say this is your machine learning or any deep learning model, and the variables that are used for tuning this machine learning and deep learning models are, let us say, W1 and W2. So what exactly you will be doing is you will be actually you know that you will be calculating the loss for this machine learning and deep learning architecture. So these gradient tapes, what it will do is it will actually be able to give you the derivative of the loss with respect to W1 and the derivative of the loss with respect to W2. So all the variables that you will be using for defining these machine learning and deep learning models, this gradient tape will be able to actually calculate the loss with respect to these variables. So we will be automatically be able to get these loss calculated using this TF dot gradient tape. And then you know that you can actually use this gradients to calculate the updates in the parameters of the variables W1 and W2. So let us take very simple examples to explain you what gradient tapes are and how it is calculated, and then we will actually continue this idea further, and we'll use it in designing neural networks and other architectures in future. So let us take this particular example. If you can see over here, we have a definition of a function W1 and W2, and these W1 and W2 are variables. So what exactly we are doing here is the function that we are defining is a function of W1 and W2, which is nothing but 3W1 square plus W1 W2. So mathematically speaking, if you want to take the derivative of the function with respect to W1, what exactly you will get is 6W1 plus W2. This is the answer that you will get. And then if you take the derivative of the function with respect to W2, what exactly you will get as the answer is W1. So these are the answers that you will get when you take the derivative of the function with respect to W1 and when you take the derivative of the loss, or you can say function with respect to W2. So let us calculate these values through the gradient tape, whether they are indeed coming true or not. So what exactly we are doing here is we are actually defining this function here, and then we are defining the variables W1 and W2, which is TF dot variable, and let us initialize them with value 5 and 6. Now we define the gradient tape, and how we will define it? We will define it like this, with TF dot gradient tape as tape. So we will use this particular way of defining the gradient tape, and then what we will do is we will actually define the loss function first. So this basically particular function, we are defining it as loss. And why we are saying it as loss? Because in most of the machine learning and deep learning architectures, finally what we are doing is we are actually calculating the loss of how this machine learning and deep learning architecture is behaving, and that behavior is actually evaluated in terms of the loss function. That's why I'm calling it as loss, and I'm calling this function fw1 w2, which I have defined over here. Now what we will do is we will just call this tape dot gradient and then loss, and then we will put in brackets W1 and W2. So what exactly it will do is it will actually calculate the loss with respect to W1, and then it will calculate the derivative of the loss with respect to W2. And then you can print the gradients, and finally you can delete the tape also. So once you delete this tape, all the gradients which were recorded in the backpropagation will all get deleted. So you can use this also to free up the memory resources. So let us run this particular code and see whether we are getting this particular answers or not. So let me put the values of W1 and W2. So W1 is 5 and W2 is 6. So if I put these values, 6 into 5 plus W2 is 6, I will get 36 as the answer. In the second case, what I will get is 5 as the answer. So let us see whether that is indeed true or not. So here you see what I am doing is I have already explained you this particular piece of code. So let me run this and see whether we are getting the same answer or not. So let me import the TensorFlow library first. So import TensorFlow STF and then let me run this piece of code. So the answer is 42 when you take the derivative of the loss with respect to W1, and when you take the loss with respect to W2, answer is 10. And please note why we are getting it different is because I have actually missed out 2 over here. So it was actually 2 here. So if I use 2 this side, so it will be 2 times 6. So what will be the answer now? It will be 42. This is not 36 because 2 was initially missed out. And here it is 2W1, so the answer will be not 5, it is 10. So you can see here you are getting 10 as the answer and then 42 is the answer. So in this way, basically you are able to calculate the derivative of the loss with respect to the variables W1 and W2. So this is one way of doing it. As I have shown you over here, this is one way of doing it using the simple with tf.gradient tape as tape, and then you define the loss and finally you calculate the gradient. Another way of doing it is you can actually use this particular piece of argument here, that is persistent equal to true. And once you use this persistent equal to true, what you can do is you can actually take the derivatives with respect to W1 and W2 using tape.gradient 2 times. The idea of using persistence is equal to true is basically you can call tape.gradient multiple times. If you do not put this persistent is equal to true here, then you cannot call tape.gradient 2 times. You can only call it 1 time. So let me run this piece of code first and then I will show you what is the difference. So here you see the answers are same, that is 42 and 10. But if you actually remove this particular piece of argument here, let me remove it and run this piece of code. So if I do this, actually what you see is a non-persistent gradient tape can only be used to compute one sets of gradients. So basically you cannot actually call these tape.gradients 2 times, you can only call it 1 time. So if I actually put this inside, let me put this inside and then run it, then what I will get is I will still get this error because it cannot calculate 2 times the tape.gradient. In order to call this tape.gradient multiple times, you have to actually use persistent equal to true. So let me make it same as it was earlier. Okay, so this is basically the idea of using persistent equal to true. So basically by persistent equal to true, if you put this particular argument in the function of the gradient tape constructor, the tape can be used to compute gradients multiple times. After you are done, you should delete the tape using the del tape to release the resources as we have done over here. So once you do this, your resources will be free. So in this way, actually you can use multiple times calculation of the gradients using, you can calculate loss with respect to W1 separately and loss with respect to W2 separately. You can actually calculate the loss with respect to W1 and W2 in one line also using this piece of code. This is just a simple example where you actually take the variable and you take the square of that variable. So it's basically somewhere or the other, it's like x square. So if you define a variable x, which is if you are defining here as input underscore variable, so what you are doing is you are squaring that variable. So obviously when you take the gradient of that result, square result with respect to the variable, you will get 2x as the answer, or 2 times the input variable as the answer. And if you have 0.3 as the initial input, so answer will be 0.6 because 2 into 0.3 is 0.6, which is the derivative of the result with respect to the input variable, because the function that you are using is square function. So let me run this and see 0.6 is the answer. Now we are heading towards something different. So this particular piece of code, what it is trying to do is it is actually trying to calculate the gradient tape with respect to the constant. In this piece of code, what we are trying to explain you is that gradient tapes, whatever we use always, it's always with respect to the variables, because variables are the ones which are changing with time. So when you take the derivative of the loss with respect to the variables, gradient tape will keep track of it. But for the constants, like if you have a constant in the loss function or somewhere, gradient tape will not be able to calculate the derivatives of the loss with respect to that constant. So this is what it is trying to show you here in this code. So what we are doing is we are defining a constant CONST1 as a constant value, and then I am taking the square of this constant. And now if I take the gradient tape, or you can say if I am taking the gradient of this result with respect to the constant, answer should come out to be none. Why none? Because as I told you, gradient tape is keeping track of the variables and not the constants. So that is why the answer is coming out to be none here. But if you want really to take it with respect to the constants, then what you have to do is you have to actually use tape.watch on the constant variable. So once you put a watch on this constant variable, then you will be able to calculate the derivative of the result with respect to the constant value. So here you see initial constant value was 4, and if you square it, obviously it will be like so let me show you here. So what I am trying to say is that if you have a function f which is defined as c square, and now if you do not use tape.watch in the gradient tape function, or you can say gradient tape constructor, then if you take the derivative of the function with respect to c, your answer will be none. Whereas if you use tape.watch with putting a watch on the constant variable, and then if you take the derivative of the function with respect to c, you will get 2c as the answer, and hence c is right now 4, so you will get 8 as the answer, which is shown over here. So the basic idea is that if you are using variables, then there is no use of using tape.watch function. But if you are using constants, then if you really want to take the derivative of the loss, or you can say any function with respect to the constants, then you have to actually use tape.watch on that constants, and then you do the then you can use gradient tapes on that. So this is basically showing you that particular stuff. So this is again I'm trying to actually show you that same example. Here right now it is tf.square, but now I am using this function f, which I have defined over here. If you see, I have defined this function f over here, 3w1 square plus 2w1 w2. So now instead of using the variables w1 and w2, I am using the constants c1 and c2. So if I do not put a watch on these constants, the answer will be none for both c1 and c2. If I put a watch on both c1 and c2, the answers of this and the answers of using the variables w1 and w2, the answers which we will get will both be same. So in this case, if you see, the answer is 42 and 10 in case when w1 and w2 are variables. But if I use c1 and c2 and put them as in tape.watch, I will also get the same answer, 42 and 10. So let me show you that as well. It's another question, it's another example. So this is what I'm trying to show you over here. So if I put tape.watch on both the constants, I will get same answer, 42 and 10. But if I comment them, so let me comment this and run it, then your answer will be none. So you see, the basic idea is to show you if you want to take derivatives with respect to the constants, you have to actually use tape.watch to make them run for calculating the derivatives. Okay, so this is actually one way of implementing the code where you are using this particular way of defining the derivatives. So here basically in tape.gradient, the result is calculated automatically with respect to the const1 and with respect to the another constant const2. However, you can actually call this tape.gradient multiple times, as I already told you earlier. But in that case, what you have to do is you have to actually use the persistent equal to true to call these tape.gradients 2 times. And the answer will still be the same. So this is another way of implementing the same idea. And then you delete the tape also to remove the resources, or you can say free the resources.